Okay, so welcome to all in sunny Cargese, and I'm Thierry Giamarchi from the University of Geneva. I'm one of the organizers, so this is a pleasure to welcome you all to this place. Sorry I couldn't be with you yesterday, but I had to teach in Geneva, so I could only arrive yesterday evening. So normally the speakers start by thanking the organizers for inviting them, so I won't do this, but I want to thank Patricia, who did really the brunt of the work for the organization of this conference. So she's the real organizer behind the conference. Okay, so my goal is to tell you a little bit about Luttinger liquids. So between me and Jean-Sébastien Co, will give you a good cop, bad cop treatment of 1D system. You have to decide who is the good cop and who is the bad cop. No, I'm joking. And so bad cop. And so this is my goal. I'm sorry, normally when I do lectures, I like to use the blackboard, but for practical reasons, because I also want to mix with experimental slides and so on, I will use slides. If I go too fast, don't hesitate to shout. If you have questions, don't hesitate to stop me. This is supposed to be pedagogical. So anytime we can switch on the lights and write on the side of the board if there is something that needs clarification. Okay, here is today's plan of lectures. So this is too late to change. But of course, these 2 points here will depend also on the other courses, will depend on what you would like to hear, and so on. So don't hesitate to tell me if you have your pet subject or whatever, and this is subject to change. But as of today, I would say for this lecture, I will certainly do equilibrium, basic notions of Tomonaga-Luttinger liquids, and then we'll move on to beyond Tomonaga-Luttinger liquids in the 2 next lectures. Okay, why one dimension? I don't think I need to answer too much this question for this audience. There are a lot of motivations which I think will be clear as we go on in the lecture, mostly that there are experimental systems that are good realization of 1D systems. But there are 3 urban legends that I would like to dispel about one dimension. The first urban legend is that one dimension is a toy model to understand higher dimensional system. Nothing could be further than the truth. 1D systems have their own lives, their own properties, and the physics which is usually markedly different from higher dimensional systems. So that's the first, let's say, urban legend that I would like to dispel. The second urban legend is that this doesn't exist in nature. This is just a game for theorists, and I also would like to blast this. And the last one is the most dangerous, but of course this lecture today will go in this direction, which is that everything is understood. It's so simple that we understand everything, and I hope that the lecture 2 and lecture 3 will convince you that there are really open problems. But of course today this will be the instrument that works, so we will follow this urban legend, but not much more in the other lectures. Okay, so why is one dimension especially interesting? You already heard probably a little bit this in the other courses, is the fact that this is the system in which particles are the further away from individual particles. If you are in 2D, like on the floor here in this room, you behave as 2-dimensional objects because you cannot go in the third direction. Even if you have infinite repulsion between you, you cannot occupy physically the same space. You can behave as individuals because you can avoid each other very easily in 2 dimensions or 3 dimensions. This is very easy. So even if you have infinite repulsion, you will behave as individual particle. As you saw last lunch, and you will see this present lunch, when you queue at the cafeteria for getting your food, there is no individual motion which is possible, only collective motion. If you try to move forward, you will push the person in front of you, will push the person in front, will push the person in front. And so one individual here cannot behave as an individual, but behave only as a collective excitation inside the system. And so one dimension is the place where individual excitations do not exist, only essentially collective one live. If you want another metaphor, I would say, cars on a highway, if you have only one lane, you move with the flow and there is no particle motion. But if you have several lanes, and assuming they are a little bit less dense than this, you can recover your individuality. Okay. The other reason is that in 1D there are strong fluctuations, quantum fluctuations, which makes that even at t equals 0, even at 0 temperature, order is very, very difficult. And most of the methods we know and love in higher dimension rest on some form of mean field theory, where we assume a certain order and then we do an expansion around it. And of course, if you don't have order, for example, for bosons, we assume Bose-Einstein condensation. So you say the wave function has an amplitude, but it has a phase, and the phase is fixed. And this is the signature of Bose-Einstein condensation. Well, at least let's say it's a signature of Bose-Einstein condensation. And then we do small perturbation around this fixed value of the phase. Well, in 1D, the phase will not order, because you have a theorem that says you cannot break a continuous symmetry, essentially. And so you have to invent other ways of treating the problem. So we lose most of our theoretical methods, and that's what makes 1D interesting. You have to invent new methods, and you heard already in the talk of JS, new methods that works in 1D, namely Bethe-Ansatz and integrability. Okay. There are many condensed matter and cold atom systems. We'll come back to those, which are pretty good realization of one-dimensional or quasi-one-dimensional systems. I won't comment much more on this slide. We'll come back to this when we discuss the consequence of the theory. And what is more important is that there was a drastic evolution of the 1D world in the last 20 years or so. This is a very old field. This is a field which started in the 1950s. Way before anybody in this room, including me, was born. But in the last 20 years, there was really mini revolutions in the 1D world. There were new methods that came out. DMRG, which is a very strong numerical method, which was invented in the 90s by Steve White, but which has known in about 2005 a second youth, which made it incredibly powerful. People could compute correlation from Bethe-Ansatz, and that you will hear more from the talk of JS, which was also something which was not done in the 70 previous year that Bethe-Ansatz was on the market. There were new systems, cold atoms, new magnetic insulators, and so on, which made it extremely stimulating to work on 1D systems. And there are new questions that people asked, strong spin-orbit coupling, and in particular, of course, something which interests us particularly for this conference, which is out-of-equilibrium properties. How to treat? Well, that's the beauty of it. So I'll just give you a little digest. Mostly this is an historical slide, if you prefer, just an excuse to show you nice pictures. So people started with standard many-body theories, diagrammatic theory, Feynman diagrams, and so on. So this is Tomonaga-Luttinger. Then you have the Russian school, which was extremely powerful, Lev Gorkov, Igor Dzyalojinsky, Anatoly Larkin, who, using brute force diagrammatic theory, managed to extract extremely remarkable results. But, you know, that's really like climbing the Mont Blanc barefooted. You really need to be skilled to do this, and that's not the right method. So this line of attack faded away. Then essentially three methods or three classes of method have emerged. Exact solution, Better-Ansatz and its derivative. I would say two heroes in that field, and I hope JS will not contradict me, are Hans Bethe, of course, because he invented the method, and Elliott Lieb is probably the most well-known person, at least connected with the field of called atomic gases, but there are many, many others that could be added on this list. There are field theories, and that's mostly what I will discuss in these lectures, a method known as bosonization, conformal field theories. And there, clearly, the three heroes are Alan Luther, the late Vic Emery, and more recently Duncan Haldane, who got the Nobel Prize for other reasons, I would say, but did extremely crucial work in this field. And then there are numerical methods. And of course, there are all the generic numerical methods that are applicable, but there is one in particular that was invented, which is by Steve White, who is here, who is known the density matrix renormalization group. And then, as I said, in 2005, both the group of Steve White and Uli Schölweck, who are here, made significant progress to this method. And what is remarkable in 1D, as you will see, is that none of this method alone is really able to cover the whole spectrum of what we need. But if you make them work together, and that's the beauty of it, in 1D we know how to make this method work semi-harmoniously together, then you have really an ultimate way to tackle and attack and solve 1D problems. So the main secret is not so much in this or that method, but is the fact that we have a multi-method attack of the problem, and then this helps really making progress. Here are a couple of references. There is also on the web, okay, if you go on YouTube, there will be a certain number of lectures on 1D that you will find that I have in particular given, but of course other people as well. There is on archive lectures of a Salerno school that you can find, which is sort of relatively light and pedagogical version of this lecture. And then here are a couple of references. And finally, I cannot, of course, not recommend you a very good book on the subject, but which contains probably more than what you want to know about 1D systems. Okay, and now let's start and go really with the heart of the problem. So the first question is, what is a 1D system? Because in a way, we live in the 3D world, so you could say it doesn't exist in our world. So there are two ways you can do a 1D system. One way is simply confine things in one of the dimensions. And quantum mechanics tells you that if you confine things in a dimension here, then the energy level will be quantized according to essentially inverse of the size here in this direction. So what you have is continuous or semi-continuous energy level with a quantum number associated with x, so kx, for example, if you have free particles. And you will have very discrete energy levels associated with the motion or the quantum numbers perpendicular. So in a way, you get this kind of mini bands here, where n equals 0 is the zeroth quantum number in this direction. 1 is the first level, excited level in this direction. And now you see that if you have fermions, for example, and you feel the band here, and your temperature or interactions are not too large, then only one of these states will be important. But of course, you have a continuum of excitation along x. So this behaves exactly like if you were strictly in one dimension. Of course, the wave function of the object are extended. They are not reduced to a single point. But because of quantum mechanics, otherwise we would not have any real 1D system, but because of quantum mechanics, as long as we don't excite the system too hard here, then we perfectly stay in the lowest band, and we have a one-dimensional system. There is another way of doing 1D systems, which I'll discuss later, which is to couple 1D units. So, for example, chains which are coupled will also behave as a quasi-1D system. So what are the typical problems that people want to deal with? Bosons in a continuum. So this is p squared over 2m. This is the wave function of three bosons. Grad psi over 2m is p squared over 2m. That's the kinetic energy of bosons. And then you put a contact interaction you put an interaction between bosons. So this is the product of the two densities with a V, and this is the chemical potential term. If you put the contact interaction here, so if V is a delta function, this is the celebrated Lieb-Lininger model of bosons with a contact interaction, and I'm sure Jean-Sébastien will tell you much more about this model. You can be on a lattice. So if you are on a lattice, you use tight binding description of the particles. And then this most famous model is the Hubbard model, or Bose-Hubbard model if you have bosons, which is kinetic energy of particles hopping on the lattice. So B dagger, which destroys a particle here, make it jump on the next lattice. And then an interaction, which here I've taken on site. So the particle only see each other if they are on the same site. You can put nearest neighbor, repulsion or attraction, and so on and so forth. So these are the typical Hamiltonians that we have to deal with, and again, the chemical potential. And of course, what makes this problem complicated is this term, because this term is a 4 fermion or 4 boson term. So this is not something you can diagonalize easily by is not something you can diagonalize easily by, let's say, a Bogoliubov transformation and so on. So how do we treat... Uh-oh, I've lost my pointer for some reason. Yeah, let me try to restart this, if I can. Close the... up. Logitech is not what it used to be. Voilà. Tac. Voilà. And now I can go very fast, hopefully. Voilà. Okay, I'm back. So now, how do we solve this problem? And the idea is, of course, you can use better ansatz for some of this model. You can use numerics and so on. And what I will describe to you is a field theory approach. So something which consider that we look at the low energy property of these models, and we try to find an effective field theory that describes this model. And the thing I will do here is to follow the way which was proposed by Duncan Haldane. There are different ways of doing it, but I like particularly this way because it shows really the physics of what we are going to do. So the idea is that in one dimension, I can always label the particles. In more than one dimension, it's very difficult to find a unique way of labeling particles, but in 1D, you start from the left, you go to the right, 1, 2, 3, 4, 5, and so on, and this is as good a way of labeling the particle than any. So instead of labeling the particle with 1, 2, 3, 4, 5, I will introduce a field, phi L, of x, and I will say there is a particle when this field is 2 pi times an integer. So the integer is the label of the particle. So when phi L is 1 in units of 2 pi, I have the position of the particle. When phi L is 2, I have another particle, and so on. So you see that if phi L is a field growing linearly, then my particles are forming a crystal, a perfect crystal. But if, of course, phi L is deformed, is something which is not strictly linear, then my particles can be everywhere I want. I just deform phi L. And when this is 1, I get the position of the particle. When this is 2, I get the position of the particle, and so on and so forth. So I can use phi L to determine the position of all the particles. Now, why is this useful? Well, it's useful because the density operator is a very unpleasant operator, which depends on the position operator of the particles, and which has a very ugly limit. It's infinity when you're on the particle, and it's 0 if you're just sideways. So good luck to take a continuum limit, a long wavelength approximation of this object. It's a highly discontinuous object. So the idea is to re-express the density operator in terms of this field phi L. And I leave it to you as an exercise to show that this is the way to do it. So essentially, the density operator will be 0 if you're not at the point where phi L is equal to 2 pi n. So there is a delta function of phi L minus 2 pi L. And then the rules of delta functions makes that you must multiply by the gradient of phi L here. Okay, so far it seems like a very complicated way of writing the same thing. Now, I will introduce another field just to get rid of the, let's say, slope that would occur with the average density rho 0. So I introduce a field phi, which is the deviation of phi L from a strict linear growth. So again, here phi for this one would be 0, would be strictly 0. And here phi is the difference between the diagonal and the curve. And you can show, again, that you can write the density in this very complicated way by using expression of the delta function, essentially, that you write the density as rho 0 minus gradient of phi times a very ugly sum, where p is an integer, going from minus infinity to infinity of these things. So far, it looks like you complicated your life rather than simplifying it. But actually, that's not true. Because you see that now what you've done is something where if phi varies slowly, if you assume that phi is slow, which means that it doesn't vary very much at the distance between two particles. Let's assume it's a constant for simplicity. You've realized a Fourier decomposition of the density. So the first term here, let's take the term with p equals 0 here. So this goes away. The first term is just the hydrodynamic version of the density. Imagine that I think of phi as the displacement of the particle compared to a perfect crystal of particle. You see that if I move this particle here towards the center, here towards the center, here towards the center, here towards the center, I've created a bump of density here. And this is exactly what this first term is giving me. So you can think of phi as the displacement relative to a perfect crystal of particles. Now, what are the other harmonics? What are the other terms here with p equal 1? Let me forget the gradient, just multiply by rho 0. You see that this corresponds to cosines, which have exactly the periodicity, if p equal 1, for example, of the particles. So what this term tells you is that if you take phi, which is constant, and you shift the particle altogether, of course your density will change dramatically because you've moved the particle sideways. So instead of having infinity here, you will get 0. But you can still compute this with a phi that varies slowly. So in a way, you have encoded the difficulty of taking the continuous limit in the density in the shape of the operator. So instead of saying, oh, I have an operator which is written simply, but which is difficult to compute, with this change of variable, you have written the operator in a complicated way, but which now is a simple function of a smooth field. And of course, that's the good starting point to build a field theory. You now have the possibility to say, oh, I will only consider slow variations of the field phi. So the field phi is essentially something that measures the displacements of the particles relative to a perfect crystal. Think of it exactly as in elasticity, the displacement of particle relative to a perfect crystal. And the point is that you can express the density in terms of this field phi. So this is the Q close to 0 component of the density, and it immediately shows you that you have higher harmonics at 2 pi rho 0, which is exactly the distance between particles in a perfect crystal, 4 pi rho 0, 6 pi rho 0, 8 pi rho 0, and so on and so forth. Okay, so this is a charge density wave. So you see that now, because all this is an operator, because phi is an operator, you see that if I say phi is ordered, phi is a constant, what I get is a perfect charge density wave of particles. So this is the secret ingredient, if you want, which then allows you to compute everything you want. It's this change of variable. It's just a change of variable, but going to the intelligent variables, which are the collective variables, which corresponds to the creation of a charge density wave of bosons. Now, that's it. Once you have this, the rest is, I would say, simple algebra, because the single particle operator is the square root of the density times the exponential of a phase. That's the most general way to write it. Now, of course, theta and phi, which is hidden in the density, are operators, but they cannot be totally free operators because the psi dagger obey commutation relations if it's bosons. So the theta is the usual superfluid phase that you would like to have for a boson. Again, it's an operator. And the fact that psi dagger and psi have bosonic commutation relations, psi dagger is a delta function essentially, imposes, that's not totally immediate exercise, but it's something that can be done, imposes that there is a commutation relation between theta and the phase phi. So the gradient of phi and theta are canonically conjugate operators, and their commutator is a delta function. So it reflects a little bit, some of you maybe in superconductivity course had these comments that phase and number of particles are conjugate variables and so on and so forth. What you have here is a little bit the expression of the same thing. If you order the phase, theta, you cannot order the field phi, which tells you that you know the position of the particles. If you order the position of the particles, then the phase of the wave function is not fixed. So this is the trade-off that quantum mechanics imposes on you. Okay, and now we have our change of variable, because we know the single particle operator as a function of theta and phi, and we know the density. And now we can take our Hamiltonians, the ones that were complicated here, and rewrite them in terms of the field phi and theta. So I let you do as an exercise to show that this is essentially grad theta square times rho 0. So this is relatively easy. That's the dominant term in the expansion. And now you see this terrifying term here, because it was quartic in the bosons. This terrifying term is now absolutely trivial, because what this term will become, if you neglect all the oscillating terms and whatever, which is what you usually do in a field theory, what this term will become is density, density, and that I will write on the board because that's the key, that's one of the key steps. Maybe that's the, so you see I have grad psi dagger, grad psi over 2m, but I know that psi dagger is roughly rho 0 to the 1/2 exponential of I theta or minus I theta. I forgot what I said. Yeah, minus I theta. So now when I do the gradient here, I get a gradient of theta. The other one gives me a gradient of theta. So this becomes essentially grad theta square times rho 0 over 2m. And now I have the other one, which is, let's say, a delta function. So this is the integral over dx of v0 over 2 times, let's write it that way, rho of x minus rho 0 square. So these are the fluctuations of the, okay, but rho minus rho 0, I know exactly, I know exactly what it is. If I neglect all the oscillations here, so if I only retain the dominant field with p equals 0, This is just grad phi's. So this is now V0 over 2 pi square integral over dx of grad phi square. So this is magic, no? Because you went from a problem which was quadratic in bosons but quartic in bosons to something which is quadratic in the phase theta and quadratic in the phase phi. And because phi and theta are conjugate fields, what you write now is an harmonic oscillator Hamiltonian. That's it, problem solved. So in 2 lines or 2 pages, Duncan Haldane solved for you the Lieb-Lininger model. And believe me, I hope that Jean-Sébastien will agree with me, it's simpler than the Bethe-Ansatz solution. It doesn't have the power of the Bethe-Ansatz solution, which gives you the solution at all the energies for the model. This is limited to the low-lying excited states. This is limiting to the long wavelengths and so on. But you see, this is really a very, very simple way of now writing these interacting models. So now you see that you have what I call pi. Pi is the grad theta square, because it's the momentum conjugate to phi, to the gradient of 2 phi. And so the Hamiltonian has a shape of an harmonic oscillator. And the coefficients here are rho 0 over 2m for the Lieb-Lininger model, and the other coefficient here is V0 over 2 pi square for the Lieb-Lininger model. Now, the idea is that there are always 2 coefficients, this one and this one. So let me reparameterize them. One has the dimension of a velocity. It's the sound velocity for the excitation inside the system. And the other is a dimensionless parameter. K has the dimension of a number. And its use will become apparent in a short moment. So the message is that you can characterize any 1D system by an Hamiltonian which has the shape which is the following: 1 over 2 pi sum over dx of u times k times grad theta square plus u over k grad phi square. And these numbers here, u as the dimension of a velocity, and k is dimensionless. And of course, they depend on the interactions, the characteristics of the problem, and so on and so forth. So before I move forward, are there questions on this? Or is it okay with the derivation? Not the details of the calculation, of course, which I didn't do for you, but that is easy to find in various textbooks and lecture notes and whatever. But the philosophy of the derivation. And again, keep in mind, phi tells you where the charge is positioned, and theta is the phase of the wave function. It's okay? Okay. Now, this parameter k depends on the interaction. If I take the Lieb-Lininger model, you see that u over k is essentially V0, where V is the interaction, the local interaction. So essentially, when this interaction is 0, I rather call it u. If the interaction is 0, this parameter is infinity. And if the interaction is infinity, you would say this parameter is 0. Actually, it's wrong, but we'll come back to this. Because to derive this, I did a lot of things which were unclean. I threw away all the higher harmonics. I only kept p equals 0 here in the derivation. So the argument for doing this is to say, oh, when I have an integral, when I have something like an integral of dx, and I have exponential of I, 2 pi rho 0x, multiplied by slow fields, this oscillates, and this averages to 0. Yeah, but I can pile up things with phase cancelling and whatever. So one could worry about throwing away all these higher harmonics, because my density is much more complicated than just grad phi. Same thing, when I told you here, I replace rho by rho 0, you could have protested. It's not rho 0. It's rho 0 times all the other terms. So why should I say this just the average rho 0? So this was worries, and people thought that maybe this result is approximate. And we'll come back to this in a moment. But what I wanted to tell is already that actually you can potentially think about this coefficient u and k and little u, the velocity, as substitute for the microscopic kinetic energy and interaction. Actually, for the Lieb-Lininger model, as we will discuss later, when the repulsion goes to infinity, this coefficient k goes to 1, for reasons that will become clear, hopefully, later. What is interesting is that once you have an Hamiltonian like this, it's an harmonic oscillator Hamiltonian. So it's immediately diagonalizable, just free bosons. Not the original bosons, but the excitations are free bosons. And now you can compute all the correlations of the problem. You can compute them at t equals 0, but you can also compute them at finite temperature, because you have a free boson theory. It's just not your original bosons. It's new excitations, which are the collective excitations, which are the sound waves inside the system. So, for example, if I want to compute the single particle correlation, roughly, if I do psi of x, psi dagger of 0, what I will have is square root of rho 0, so I will have twice square root of rho 0, so I will have rho 0, and then I have to do the average of exponential of I theta of x, exponential of minus I theta of 0. Because I have a quadratic Hamiltonian, this average is exponential of minus 1/2 of the average of the square. That's a generic property of quadratic Hamiltonians. And then, since I have free bosons, I can easily compute this average. I won't do it here, but trust me, this can be done. And this is the result. So what you find is the following behavior. You find that, for example, the single particle correlation function, where you create a boson at point 0 and you destroy a boson at point x, is actually decreasing as a power law with an exponent which is totally controlled by this dimensionless parameter k that is in the Hamiltonian. This alpha is an ultraviolet cutoff. This is a field theory, so it's not valid to arbitrary high energy. So you have to put a cutoff somewhere, and you say, I only consider k momenta which are below than certain maximum momentum. And if you say that the maximum momentum, lambda, is essentially 1 over a distance alpha, this alpha is the thing which appears here. View it as a lattice spacing, if you imagine, but not the real lattice spacing. The upper momentum in your theory defines a kind of length in your chain, which is several lattice spacing, for example. So this is your ultraviolet cutoff, the cutoff at high energy that you have in a field theory. So you see that the single particle correlation here is decaying as a power law with an exponent which is controlled by this parameter k. So first, it tells you that it's not ordered. There is no perfect superfluidity in this problem. It doesn't go to a constant. And second, you know exactly how it decreases. It's quasi-long-range order with a power law decay. Same thing for the density-density correlation function. Forget y, this is the time. So let's set y equals 0. So there is a part which decreases as 1 over x squared. But there is, more importantly, an oscillating part which decreases again as a power law, but this time with another exponent which is also a function of the parameter k. What does it mean to have this oscillating term? Well, it means that you have a charge density wave. So if you look at what it means that if you know that you have a particle at point 0, then if you had a perfect crystal, you know exactly where are the other particles. So if you have a density which is oscillating like this, so if you say I have a density which is rho 0 cosine 2 pi rho 0 x, it means if you know you have a particle here, which is what this operator is doing, then if you look at the operator at distance r, you know exactly that you have all these oscillations of the density. What the fact that you multiply this by a power law means is that it's not perfect. There are fluctuations, and after a while you lose the signal, but it's practically a very good charge density wave. So you see that interacting 1D bosons are both very good superfluids. They have a superfluid order that decreases as a power law, and they're also pretty good charge density waves. So they are pretty good crystals of bosons with a period which is their natural period, because both decrease as a power law. Now, of course, if k is large, this is a very small power, so this practically doesn't decrease, while this decreases super fast. So if you remember that k is proportional to u, at small u at least, then you would say that at small u, the superfluid order, quote, the superfluid decay is dominating over the density, and at small k, this is the opposite. So you can do a kind of pseudo phase diagram. It's not a real phase diagram, but you can do a pseudo phase diagram where you would say as a function of k, I have here a superfluid. I'm dominated by superfluid fluctuations. This is if 1 over 2k is the smallest exponent. And when I go here, I'm dominated by charge density wave fluctuations. And the transition occurs, let's say the change of behavior occurs when k is equal to 1/2, when these two exponents become equal. Again, for reference, the hardcore bosons, as we will determine later, is corresponding to k equal 1 here. Okay, so we sort of solved the Lieb-Lininger model, and I want to show that this field theory solution is coinciding very well with exact solution that Jean-Sébastien has obtained, and I'm sure he will talk much more on this in his lecture, so I don't go too much. What we have here with this solution is, of course, not all the spectrum, but just the low energy part of the spectrum, so the part which is here, and more importantly, the part which is here at low energy. That's what field theory are good for, is to give you the low energy part of the spectrum. I already mentioned it. You can do the calculation at t equals 0 at finite temperature. Just for the record, this theory is conformally invariant, and therefore you can also use conformal invariance to extract the finite temperature, because being at finite temperature is like being on a torus in the time direction, in the imaginary time direction. And this power law becomes, by conformal transformation, an exponential. When you reach a thermal length which is proportional to the inverse temperature, all correlation starts to decrease exponentially fast. You lose now, because of the thermal fluctuation, you lose the order much faster. If you want, your system becomes 1D classical, and you know that in 1D classical, you lose correlation exponentially fast. Now, there are other 1D systems than bosons, but they are very easily connected to the bosons, so we don't need to do anything special to this. For spin 1/2, you can either map the spin 1/2 to bosons, or you can map them to fermions. To fermions, it's called the Jordan-Wigner transformation. I don't know if Jean-Sébastien has or will talk about it, but let me give you the transformation for bosons. That's very simple, much simpler than for fermions. So if one day you want to map spin to bosons, the only thing you have to do is to say the following. You just, maybe I should keep the light on, is to say that the S plus operator is like creation of a boson on the site. The S minus is like destruction of a boson on the site. And SZ is just counting the number of bosons minus 1/2. And you can check that this will satisfy the bosonic and the spin commutation relation, spin 1/2 commutation relation. Now there is a catch. A spin 1/2 has only two states, down and up. So for the bosons, you can only get 0 or 1. But if you have bosons, you know that you have, in principle, many other states. So for bosons, not for fermions, but for bosons, you need to cut the Hilbert space. The way you cut it is by putting an infinite repulsion on site for the bosons. So if you want to do this, you need to have hardcore bosons, which means you add to the Hamiltonian a term which is U over 2, sum over J, Nj, Nj minus 1, which ensures that if you have 0 bosons, this is 0. If you have 1 boson, this is 0. But as soon as you will get 2 bosons, this is finite, and you let U go to infinity. If you do this, the mapping between bosons and spins is perfect. To avoid this constraint, you could map to fermions. Fermions have this implemented automatically with the Pauli principle. The catch with fermions is that 2 spin operator on 2 different sites commute. Fermionic operator on 2 different sites anti-commute. So there is another price to pay in the mapping, which I won't discuss, and it's called the Jordan-Wigner transformation. So here I stick to bosons. So if you take my little formulas for the bosons, it's easy to check that you can rewrite the spin operator like this. You can rewrite SZ like this. It's the same field phi that I discussed before. And then you can say that you take from what I showed you before, the SZ-SZ correlation. They decay exactly the same way, 1 over x squared plus the oscillations, which if you have a non-magnetized spin chain, the periodicity is pi, down, up, down, up, down, up. So this is minus 1 to the x, 1 over x to power 2k. Okay, this is a little bit more complicated, and I don't want to discuss it in great details, but this is essentially the same power law than you got for the let's say the psi dagger psi. This is 1 over 2k, and this is the 2k, which correspond to the density wave. Now, how can I see from this that if I have an infinite repulsion between the bosons, k must be equal to 1? That's a non-trivial exercise. I'll let you think 2 seconds. Think about spin rotation symmetry. I'll not discuss it now, but spins, you know some symmetries they have. So you can use this to extract some of the things. Fermions. How can we do the same trick with fermions? Well, that's easy. I have the expression of the single particle for bosons. I want to transform it into an expression for fermions. To go from bosons to fermions, the only thing I have to do, everything else is the same. But the only thing I have to do is to make sure that now the single particle wave function for fermions is anti-commuting, while for bosons, I have something which is essentially commuting. Okay? So I need to do something from this expression so that if I write psi f equal blah blah, I get the extra minus sign to transform the commutator into an anti-commutator. And you can check that if you multiply the operator of bosons by exponential of I 1/2 of psi L of x, this does the job. So again, that's an exercise. Take it as an exercise that if you do this, you will find the proper anti-commutation relation. And so this is particularly simple because now you see that the only thing I do when I multiply this by this phase factor is to change the number here, which was in the exponential, by 1. So if I have fermions, I have exactly the same expression than I had for bosons for the single particle operator, except instead of having 2p here, I have 2p plus 1. The density is, of course, exactly the same. It doesn't change. It's the same expression. Now, this has consequences. If I add 2p, I had a term here with p equals 0. And the term with p equals 0, everything here in the exponential was disappearing. Okay, so for bosons, the dominant term, which was p equals 0, was this one. For fermions, if you take p equals 0, this stays, and you get the oscillating factor. If you take p equal -1, this also stays with a -1. So there is no way for fermions you're going to make the exponential disappear. Go ahead if you have a question. I'll gladly answer. Okay. So you see that this semi-innocent transformation here has the important consequence that now you can never get rid of the exponential for the fermions. And as a consequence, you can define the dominant operator is the one for which the term in the exponential here is either +1 or -1. And you see that now it oscillates with exponential of I pi rho 0 or exponential of -I pi rho 0 x. Now, if you have a certain number of fermions, it's very easy to check that this is Kf. So these two terms here are essentially terms that represent oscillation at exponential of ikfx and exponential of -ikfx. And this is the psi dagger fermion of x. So you can say that you can decompose the psi dagger fermion of x into two components, one which had oscillations around kf times slow fields, which you call the right movers. So this is slow fields. And another part, which is another expression here, which you will call the left movers. And again, this is slow fields. And that fits very well with the fact that for fermions, you have here 2 points close to the Fermi surface, where essentially you could say that these things here are right movers, and these are left movers. So this formula naturally introduce what you would have written by simply saying if the important excitations are the one around the Fermi surface for fermions, I have two disconnected parts of my Fermi surface in 1D, which again is different from 2D. In 2D, this part connects. In 3D, same way. You cannot separate one point of the Fermi surface from another. But in 1D, if you're on this side, you have a sea of occupied states here, which completely separate the excitations from the other side. And this you can call right movers. This you can call left movers. If you prefer, you can replace the original kinetic energy by two independent branches here. A cutoff, an ultraviolet cutoff, minus lambda, 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 minus lambda. And then you say, oh, I have here left and here right movers. And this comes directly out of this expression. So again, you can compute the density. The density has exactly the same expressions. Let me forget about this. It's not really important. And of course, if you compute the single particle function now, the n of k, which is the Fourier transform of psi dagger f psi f, now there is difference, which is the fact that there are this oscillating factor. So instead of having a power law at k equals 0, essentially, you will have now a step function or something which is a power law equivalent of a step function with a singularity at kf, which is resulting from the power law that you would expect for this system. I don't want to insist too much. I don't think it's really important. Now, before we go to experiments, the question is how much of this is true, of what I told you? How much of this is resting on this assumption that when I write the Hamiltonian, I can throw away all the higher harmonics and blah, 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 and I have this sort of free boson Hamiltonian, and I can be happy with that. And until the 80s, people were dancing from one foot to the next on this, saying, yeah, but you know, it's valid when u is small, because you can throw away the higher terms because they would be even smaller and whatever. And but you know, it's true, but it's not completely true. And what was true and what was not true, people didn't know really. And then came Duncan Haldane, and he said, okay, look, this is exact. Provided you use the correct value of u and k. So this field theory describes all, I'm lying, but okay, all the low energy property of the problem correctly, including the connection and the relations between the exponents. Because you see, now I have connections between exponents of various oscillations. The oscillations at 2kf, 4kf, 6kf, they all come from one single number, this number k. So you could say, maybe it's wrong. Maybe I need a second number or third number or fourth number. And what Duncan Haldane told you is, no, you only need two numbers, the spin velocity, which is boring because it just relates space and time, x equal ut, so you don't care. And you just need the second number here. With the second number, once you've determined, and that you need to determine exactly, not perturbatively. But once you determine this number exactly, you can inject in the field theory, and the field theory will give you all the power law decays of all the correlations you can compute correctly with the right exponent. What the field theory will not give you correctly are the amplitudes, of course, of these power law decays. So here, for example, this amplitude is non-computable from the field theory. This amplitude is non-computable from the field theory. In any case, you see that the ultraviolet cutoff is entering, and this cutoff is relatively arbitrary. You just decide you cut here, but you could have cut here, for example. We'll come back to this. But for the moment, take what I'm saying is that you need to use the exact u and k, but you see now you get a fantastic weapon, which is that you get this very simple field theory, which allows you to compute a lot of things, and the difficulty has been reduced to getting the right number u and k. And so all the properties, all the physical properties that I just described to you, power law decay of the correlations, these oscillations where charge density wave and superfluidity, blah, blah, are also a power law. This is now a common properties of all or most of the 1D problem, and they got a name. They call Tomonaga-Luttinger liquids, and this works for fermions, bosons, spins, and so on and so forth. And this is the same unifying concept than Fermi liquid was for repulsive fermions in 3 dimensions, as was derived by Landau in the 60s. So this is a remarkable achievement, and the fact, realizing that the field theory is essentially exact, and that the only thing that needed to be computed are the Luttinger parameters. This U and K was, of course, absolutely key step in all the developments that followed and which allowed to solve. So here is the seminal paper by Duncan Haldane where he derives this. This was done in 1980, and he shows this for the Heisenberg chain. So here are his plots. This would be a more modern way of putting it, where you can derive. So the way you do it, how do you get these exponents? Haha. That's the complicated. How would you get them? How do you get these two parameters? You take two physical quantities and you compute them with an exact method. So for example, you take Bethe-Ansatz. Bethe-Ansatz is not so good to give you the correlation functions. You have to sweat very, 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 very hard. But it's very good to give you thermodynamics. So this parameter U and K, they enter into the compressibility and they enter into stupid charge susceptibility or whatever. You take the Bethe-Ansatz solution, you get your U and K, and then you can compute the correlation function easily. Or you do numerics. Numerics is not so good to give you correlation functions either, because you get finite size effects and it's tough. No, you can do it better because you have 100 sites. But imagine you need to compute very long distance correlation, it's hard. But computing thermodynamics with numerics is boring. You can even do it with exact diagonalization on 16 sites. So you take the numerics, you compute the compressibility, you compute the susceptibility, and you extract your exponent. And then you compute the correlation function from the field theory. So that's what I meant when I say you can make these methods work together. You can get each method work in the field where it's strongest. The field theory is very good to give you asymptotic properties, but it doesn't know which parameters to put in its own theory. Numerics or Bethe-Ansatz, they are super good if you know the microscopic model, but they are more limited in what they can give you. But you don't care. You just need two physical quantities and you can calibrate your field theory. So this is something which was a remarkable achievement. Okay, here is another example of calculation of U and K that we did with Sriram Shastri a couple of years ago. But that's the very, very, very important idea, that you can do quantitative calculations. And the trick is to use thermodynamics and Bethe-Ansatz, to use numerics and thermodynamics, or correlation functions. It depends on the method you use. People who do quantum Monte Carlo, they are happy with compressibility and twist in the boundary conditions. That gives them two physical quantities. People who do DMRG, they are usually in a box. So twisting the boundary condition, not so great. So they compute boring, simple correlation functions, equal time, you know, the simplest one you can imagine. They fit the Paolo decay, and then they get K. And then you can get the time-dependent correlation function from the field theory. So this is, again, trying to use each method where it's strong. And, for example, compressibility gives you U over K. Response to a twist in boundary condition gives you U times K. Specific heat is the temperature divided by the velocity, etc., etc., etc. You can also use common sense. For example, imagine I have bosons, and they have an infinite repulsion, which is called the Tonks limit. Well, if I have infinite repulsion in 1D, it's like having fermions, because I have like the Pauli principle. I cannot put two particles on the same side. But it's not fermions, because the wave function is still totally symmetric for bosons and totally anti-symmetric for fermions. But if I look at density, it's the square of the wave function, so I don't care. I have minus sign, it's disappear. So the claim is that if I look at the density of bosons with infinite repulsion, it should be the same than the density of free fermions. Free fermions, I can compute the density-density correlation function. That's cosine 2kf x times 1 over x squared. That's an absolutely trivial calculation that can be done by 101 solid-state physics students. Now, remember, my density was cosine 2 pi rho 0, 1 over x to the power 2k. So it immediately tells me that k equal 1. I don't need to do any complicated calculation. For infinitely repulsive bosons, if I believe to the formula that I given you, if I want to match free fermions, k equal 1. And you see that this is very, very different from what I would have gotten naively from the perturbative formula, which tells me that k is 1 over u. Because then if I set u equal infinity, I would have set k is 0. So hence the importance of doing this exact determination of the parameters. But once you've done this, everything else will work. Okay, so this is the important point. You can also take 2 experiments and get the parameters from the experiment. You don't even need a calculation. If you have possibility from the experiments to determine 2 correlation functions, you can do it. Note that the single particle correlation of bosons, even at infinite repulsion, is highly non-trivial. It's not, of course, the free boson correlation function. And the Luttinger liquid theory will tell you that this decay has 1 over x to power 1 over 2k. So if k is equal to 1, this is 1 over square root of x. So this is a very specific prediction. And the recent calculation via Bedhorn-Zatz fully confirmed this prediction of the field theory. But that's something that can be relatively easily done. Okay, so let me show you a couple of examples, flash a couple of examples of how we can test this physics experimentally. And this should cover 10 more minutes that I have. I think we finish at 15, no? 15, yeah. So, okay, so the first example of 1D materials were the so-called organic conductors, the so-called Bechgard salts, which are made of stacks of molecules that pile up here perpendicular to the screen. And the motion of the electron is so much more easy in this direction than it is to jump from here to there that you can consider them as 1D material. We'll come back to 1D versus quasi-1D, but not in this lecture. And here is a measurement of the frequency-dependent conductivity in this material. You see various materials here. And if you use Luttinger liquid theory for computing this quantity, you will find a power law, no big surprise. You will find a power law with an exponent, which again depends on k, this parameter k. And lo and behold, when you take the experiment, you see very beautiful power law of 1 decade, which is the confirmation, and to the best of my knowledge, the first observation of a Tomonaga-Luttinger liquid in a metallic system. Cold gases were fantastically good in probing for one-dimensional physics, so let me flash a couple of experiments. This is one done in the group of Dave Weiss. You probably heard already of Dave Weiss via the quantum Newton cradle. If not, you will, I guarantee, in an out of equilibrium conference. But this is where they wanted to observe the Tonks-Girardot gas, which is the gas of bosons with an infinite repulsion. And I won't go too much in details of these curves, but what they realized here is to measure essentially the way the energy of the gas vary as a function of the repulsion. There is here a corresponding experiment that was done in the group of Emmanuel Bloch, where they realized 1D tubes and then tried to measure the single particle correlation function in this tube. So this is the Fourier transform of it, n of k as a function of k, and normally it should follow power law of k, which is the Fourier transform of 1 over x to the power 1/2. Now you see it doesn't really follow power law. It seems weird. And the reason it's weird is one of the biggest problems of cold atomic gases is that everything is in a parabolic trap. And this parabolic trap makes the density highly inhomogeneous. Now people have boxes, so this is much better. But in 2004, this was very difficult because the trap, which is schematized here, makes you a density which is highly inhomogeneous. So you need to extend this theory to inhomogeneous density. So if you're in the free fermion limit, that's relatively easy. And that's why the theoretical curves are in good agreement with the experimental one. But we are far from the idealized Luttinger liquid prediction. But it's still something that tests this 1D physics. Here is the group of Jörg Schmidt-Meyer in Vienna, where he used atom chips, so he can realize two 1D gas. Then he let them fall, they interfere, and when they interfere, he measures by simply projecting light the interference pattern, and this gives him access to this correlation. This is the integral up to a size L of the single particle correlation. So this should have been a Paolo, but he's at really high temperature. So this is actually an exponential, as we discussed. But this exponential depends on the parameter k. So you can test that indeed this is in decent agreement with the Luttinger liquid prediction. And this was done by the late Adilet Imambekov, Vladimir Gritsev, and Eugene Demler. This is a very nice thing. You can also measure the velocity u. I won't go in detail. This is measurements that were done in the group of Randy Hewlett in Rice University, and we help, and particularly Piotr Grissins helped with the theory. So this is a 1D Fermi gas, which is a realization of a model which maybe JS will tell you about, which is called the Godin-Young model, which is interacting fermions in one dimension, essentially, on the continuum. And by using a special technique, which is Bragg spectroscopy, they could measure here peaks, which are sort of telling you what is the velocity of excitation. They do an excitation at energy omega, at momentum k. So omega is uk, so when you get the peak in the absorption, it means that this is the frequency. This is the velocity, and so you can map for various interactions. They can change the interaction by turning a knob in the lab. You can map the dependence of the velocity as a function of the interaction, and this fits reasonably well what are the predictions, the theoretical predictions, which made someone tell in one of these gossip journals that ultra-cold atom confirm 50-year-old physics theory. You can take it as a compliment or as an insult, depending on how you are. Okay. There are other very important properties, and one that I really want to emphasize, because it's really important, is the fractionalization of excitations. So imagine, let me take an antiferromagnet, for example, as described by an Heisenberg model, and imagine that I try to create an excitation by flipping a spin. The minimum excitation I can do is flip one spin 1/2. So the minimum quantum number I can get is delta S equal 1, minus 1/2 to plus 1/2. And you cannot do less than that. So here it is. Okay, here I do it in the opposite direction. So I have a quantum number minus 1, and that's the minimum I can do. And in 3D, this excitation is called a magnon, and it propagates. Okay, here I created it locally, but if you do Fourier transform, it has a well-defined momentum q, and it will have a well-defined energy as a function of this momentum q. So it behaves as a particle, and that's why you put O at the end. It's a magnon, a magnetic excitation, magnetic quasi-particle. Well, in 1D, things happen a little bit differently. Let me do the same thing. And now let the system evolve according to Heisenberg. There are S plus, S minus terms. So I flip spins, I flip spins, I flip spins, and then you see what happened. In this region, now I don't have 3 spin down close together. I only have 2, and I have a string of spins turned in the wrong direction. They just flipped compared to their initial position. And it reaches a place in the system where I get another region where I get also 2 spin down together, and then things go back to the way they were. So my magnon has split into two excitations here. But these excitations are non-local. They are not like the magnon, something really local, but they carry behind them a string. But in 1D, the string has no cost. It can go as long as you want. And these excitations have a name. They are called a spin-on. And if you work out their quantum number, they carry spin 1/2. So this is a very weird situation where a local excitation has decomposed into two collective excitations, but with a quantum number, 1/2, that should have been impossible to reach. It's just because you pushed 1/2 to infinity in a way, okay? So they are created in pair because they should correspond to a physical quantum number, but you see that they can deconfine and separate into two entities that will live their lives. And this must have consequences. And the consequences are the fact that these non-local excitations can exist, as I said, in pair, if you create them from a physical probe. These have hidden topological order parameters, because you see the phase of the spin order here is opposite than the phase of the spin order here. So if you classify by phase at each end, this has a topological index that you cannot relax. And instead of a well-defined relation between momentum and energy, now you can split the initial momentum into two momenta. Each one will be carried by one of these excitations. They have, let's say, a cosine dispersion relation. So you see that now the energy is the sum of two cosine with an arbitrarily split of the momentum. So you will get a continuum of excitation instead of having a nice, well-defined relation between the initial momentum and the energy. So the creation of this deconfined excitation is the rule in 1D, not something which is the exception. And this has observable consequence, even if you probe with local probes, even if you probe things that you can see only with a physical probe. Let me just say what happens if you have speed and charge. It's exactly the same thing. If I remove an electron, which carries a charge and a spin, after a while, the excitation will propagate, and you will have a place where no charge is missing, but you get the two spin down, so you get the spin on, and this string of overturned spins. And now if I let the charge propagate, I will have another region where you see that this is up, down, up, down, up, down, but the charge is missing, so this excitation has been called a holon, and you get a string here between spin-on and holon, and this holon has deconfined from the spin-on and carries charge but no spin, and the spin-on carries spin but no charge. How can you probe this? That's difficult because you need a local probe. If you have only a local probe, like you have, for example, in condensed matter, well, you see the indirect consequences of this spin-charge separation or deconfinement of excitations. But if you have the chance to have a non-local probe, and this is something that people can get in cold atoms because they can see, they can take a photograph of the whole system as a whole, then you can check that indeed this is what happens. So these are experiments that were done in the group of Emanuel Bloch in Munich, where they can take an image of the 1D chain, and then they can resolve in spin. So here on this side there is nobody, here on this side there is nobody, here on this side there is a spin down, now there is a spin up, now there is a spin down, now there is a spin up, down, down, up, and so on. And so they can test this theory that there is indeed the splitting of a single excitation into spin-on and holon, and that confirms very well the predictions of the, I would say, 1D theory. I won't go into the details of what they really observed, but that's just to show you this. Here is a blow-up of the image. So, for example, here is a spin down, a hole, up, down, up, down, up, down, up, down, another hole, and so on. So you can check that the hole is surrounded, the holon is surrounded by down, up, down, up, down, and so on. And that this is creating phase defects from a perfect antiferromagnetic chain. So this is something that can be tested if you have a non-local probe, if you have something that can give you the whole image at the same time. Now, just to finish, and then we'll see the rest not tomorrow, but on Thursday. What happened of this deconfinement if you're in higher dimension? Well, it doesn't work. Because if I try to do the same thing, then I will make the thing move. But you see that the string now has a cost, because the neighbors don't like to have the spins in the wrong direction here compared to up, down, up, down, up, down. So now when you try to deconfine the charge and the spin, you see that you have an energy cost that grows with the distance between the spinon and the holon. And that's like for quarks, you're confined and you cannot separate the spinon and the holon, which means you get the spin degree of freedom will go together with the charge degree of freedom. And that's what you would call a Landau quasi-particle. That's an electron, if you want. So this mechanism, these things are very specific to 1D, and they would not easily be transposed in higher dimension. Now, there are other mechanisms in higher dimension that could lead to deconfinement and so on, but this is sort of the rule in 1D and not the exception. So let me stop here. We'll continue next time with showing you some example of quantitative solutions for the Luttinger liquid, so places where we could quantitatively compare the field theory with the experiments, and then we'll try to go beyond Luttinger liquids, because as I said, here I give you the impression that everything is understood, but this is just the stepping stone on which you can tackle more complicated problems, out of equilibrium problems, disordered problems, coupled chains, and so on. And there we need you because the field is really not understood. So I stop here and I thank you for your attention.